Alright, so for this time, we are going to cover Unit 6C. This is dealing with the normal distribution. Now, a normal distribution is a very specific type of distribution, and so what we talk about today only applies to a normal curve. If it is not a normal curve, then nothing that we say today applies to it. Okay, it's really only applying to normal curve, and it'll say specifically in the problem, the following is a normal distribution, or the following is a normal curve, or the following follows a normal pattern, something like that. They have to have the word normal in there to let you know specifically what we're dealing with. All right, so what is a normal curve? Well, it's a systematic bell-shaped distribution. Okay, it goes up, it peaks, it comes down, it has a single peak. The mean, the median, and the mode are all the same. Okay, and it is symmetric. The left side is the same as the right side. If I fold it in half, there's that line of symmetry. Okay. The deviation can be different. It can have a large deviation or a small deviation. Okay. But it's either way with both A and B. It needs to have one peak, symmetric, and the mean, the median, and the mode all have to be the same. So we have the normal curve and we have the paranormal curve. Do not just confuse the two of them. And a lot of times your grades are distributed on the curve or something similar to it. So you can grade your eggs on the curve as well. All right, so what satisfies as a normal curve? So the majority of the data values are clustered near the mean. That's what gives it a very well-defined single peak. Okay, the data values are spread evenly among the mean. That gives us it's symmetric. And large deviations from the mean become increasingly rare. Okay, the further you get from the mean, the less likely something is going to happen. And there are multiple factors involved, genetic, environmental factors, which will then affect the data values. And the more factors, the less likely you are to have an outlier or an extreme value. Okay, so in 1846, there was 5,738 Scottish militiamen, and they had their chest sizes measured. Because why not? And that would be in graph A. And in graph B is the population densities of the 50 states. So the question is, which one is normal and which one is not? All right, so graph A is our Scottish militiamen. Okay, as you notice, the data is clustered together around 40, 39, 40. Even the values close to it, 37, 38, 41, 42, are much more likely. And the more you go into the extreme, the less likely the values are. Okay, there's not a lot of 35-inch chests. There's even fewer 33s. By the time you hit 44, 45-inch chests, they've kind of they've not slimmed down, they've become less likely. And while there are a couple at 47 inches, there are not very many. Okay, that would be a normal curve. And once again, it is not a perfect data fit. Okay, some people might look and go, well, it's not exactly symmetric. Once again, real world data doesn't match our mathematical model perfectly. Okay, it's going to be close. It has a single defined peak. Everything's kind of gathered towards the middle. The mean, the median, and the mode are the same. And for the most part, it's symmetric. There's also a lot of factors. You have genetics, you have environment, you have eating, you have occupation. So there's a lot of factors that went into the chest size of the militiaman. Okay, hence a likely normal curve. All right, the population density for the states. While I do have a single well-defined peak, however, this is not symmetric. This is skewed to the right. Okay. Most states have fewer than 200 people per square mile. And the further you go, the less states that there are. So while A is a normal curve, B is a right skewed curve. Okay. And once again, we are only dealing with normal curves on here. If it's not normal, none of this works. Performance reviews. A lot of test scores, performance reviews, high school teacher reviews, or not high school, all teacher reviews in North Carolina fall along a normal curve. So if everybody's about the same, they're going to make up stuff to distinguish one person from the other. And if you have to, live your life to the right of the bell curve. All right, standard deviation on a normal curve. Because the normal curve has certain characteristics, we can predict what percentage is going to fall within 1 deviation, 2 deviations, 3 deviations, so on and so forth. Okay. So 1 deviation will contain about 68% of the population. It's actually 68.3, but for this assignment, we are going to call it just a straight 68. 95%, okay, actually it's 95.4, but for these assignments, we're going to go 95%, fall within 2 deviations. And 99.7% of the data points will fall within 3 deviations. Okay, those numbers do not change if it's a normal curve. Okay, once again, not a normal curve. It's going to have different rules for the percentages, but for a normal curve, those are going to stay. So this is what the percentages will make. Remember, you got the mean, the median, the mode, which means 50% are above the average, 50% are below average. Okay. So if I take my 68% and I break it into 2, 34% are going to be above the mean, but within 1 deviation, and 34% are going to be below the mean and within 1 deviation. Between 1 and 2 deviations, if I take 95 minus 68, I get 27. Divide that in half, I get 13.5. So 13.5% of the population is going to be between 1 deviation and 2 deviations, and 13.5% are going to be between 1 deviation and 2 deviations. Okay, remember, it's symmetric, so the percentages above is going to be the same as the percentage below. All right, 99.7 minus 95 gives us 4.7%. If I take half of that, I get 2.35. So 2.35%, it falls between 2 deviations and 3 deviations. And since 50% was above, I can take 50 minus 34 minus 13.5 minus 2.35, and I'm left with 0.15% of the population will be above 3 deviations or below 3 deviations. Okay. Those numbers, those percentages do not change. So I would recommend every time you see a normal curve, you go ahead and write the graph out. Put whatever the mean is in the middle, add up your deviations, and then put your percentages. All right, so we have 2-year-old Ford Fusions. The average price is $17,500. We have a standard deviation of $500. So the first thing I'm going to do is I'm going to make a little chart. So in the middle, for the mean, the median, the mode was $17,500. And then we added the standard deviation, in this case, $500. So we added $500, we got $18,000. We added another $500, we got $18,500. We added another $500, and we got $19,000. Those are my 3 deviations above. Then we do 3 deviations below. So 17,500 minus 500, 17,000. Minus another 500 is 16,500. And subtract another $500, I get 16,000. So the mean goes in the middle. We added 1 deviation 3 times, 3 different occasions up. We subtracted a deviation 3 different times for the way down. And then it's just a matter of putting in the percentages. So 34, 13.5, 2.35, 0.15. Okay, the pink graph and the black percentage numbers are never going to change for a normal curve. The only thing that you're going to change is the red numbers at the bottom. Okay, that's your mean and then your deviations. Those will change. Everything else stays the same. So the first question is, how many people paid between $17,000 and $18,000? I just add them up. So starting at 17,000, I've got 34. Go another 34. That's 68%. 68% of 10,000 is 6,800 people. How many people paid less than 17,000? So I start at 17,000 and then I just add the numbers below it. So 13.5, 2.35, 0.15 gives us 16%. 16% of 10,000 is 1,600 people. And how many people paid more than $19,000? So go to 19. I have 0.15% left. So 0.0015 times 10,000 means there was 15 people that paid more than $19,000 for their 2-year-old Ford Fusion. All right. SAT is a bell curve. We're going to get to that a little bit more in a second. But this guy's strategy, if you're average, hey, you can look down on everybody. And if you date a statistician, well, you know, you're 3 deviations above the norm. It's a nice place to be. You're better than 99.7% of the population. Now, one thing I get asked over the years is, why don't you curve our scores? I get students will ask me that all the time. Do you curve our test scores? Do you curve our class scores? No. And they want to know why. Well, here's why. Okay. If I was to make these a true score, the number of students who get an A needs to be the number of students, same as the number of students who get an F. Number of B's has to equal the number of D's, and everybody that's left gets a C. Doesn't seem like a very good system where somebody has to fail. So I would prefer the system where everybody has a chance and everybody can pass. And what you do is set up on your own. I am not going to make a system up where somebody has to fail in my class. That's just my personal thing. But that's what it means to grade on a curve. All right. Well, the 68, 95, 90, 97 rule works really well if you are dealing with 1, 2, or 3 standard deviations. Unfortunately, not everything comes in nice round 1, 2, or 3 whole numbers. Sometimes you're going to get different values. If you have the SAT, well, let's take it back. Let's go back to the cars. You have 17,000. The next one up was 17,500. There are going to be values in between that people pay. Okay, so it's not like if you paid $17,200, we don't know what to do with the number to put it on a deviation. It's just, oh, it's not an exact deviation, so it's not going to be a 68, 95, 99.7 rule. So if you get something outside of those deviations, we're going to find out the standard score. This is known as your Z-score. Okay. Very simple formula. You take the data value minus the mean and then divided by the standard deviation. Okay. The z-score for the mean, the median, or the mode is 0 because you know 0 deviations. If you have a z-score of 1.5, that means you are 1.5 standard deviations above the mean. And if you have a negative value score, say 2.5 or 2.4, then you are 2.4 standard deviations below the mean. Okay. You can have positive scores, that's above the mean, negative scores below the mean. All right, so IQ, normally distributed, has a mean of 100 and a deviation of 16. We're going to find the z-scores for 85, 100, and 125. All right, so to find the z-score for 85, we would take 85 minus 100. That would be negative 15. Negative 15 divided by 16 is negative 0.94. So it's negative because you are below the mean, and 0.94 tells us that you are 0.94 standard deviations below the mean. All right, the mean was 100. That means the z-score for 100 is 0, because 100 minus 100 is 0. 0 divided by 16 is 0. And if I'm looking at 125, okay, 125 is bigger than 100, so it's going to be a positive z-score. 125 minus 100 divided by 16 is positive 1.56. So if you have an IQ of 125, you're a 1.56 standard deviations above the average. All right, we have a psychology test. The scores are normally distributed. The average was 65. Standard deviation was 8. What's our z-score for 55? So 55 minus 67 is negative 12. Okay, you are below the average, so it's going to be a negative score. Divided by 8, negative 12 divided by 8 is negative 1.5. And if you would like to work on this with the homework, we're going to do a distribution. We want an average of 81.079, mean a deviation of 5.742, give partial credits, and it's true-false, sir. And you probably get this one too. That little sweet spot trying to determine how long to respond to an email or a text. If you respond too fast, it's do you sit in your inbox all day? If you take too long, it's don't you ever check your email? All right. A percentile is the data value of the percentages that are less than or equal to whatever score you had. So if you've gone to the doctor's office or you've taken kids to the doctor's office or siblings or something like that, they usually take a height and weight and they will give you a percentile. So if they come back and say your child is in the 45th percentile for height, that means that 45% of the kids at their age are either the same height or shorter. Okay, same thing for weight, for BMI. You'll see it on test scores. You'll get your score and then you'll have a percentile. It tells you the percentage of kids that scored the same value or less. And this is the chart. Okay, you have a z-score and then you have a percentile that goes with it. So if you are 0.7 standard deviations below the mean, that would be a z-score of negative 0.7, and you would fall into the 24th 0.2 percentile. Okay. All right. Cholesterol levels in men from 18 to 24 has an average of 178, a deviation of 41, and there's that keyword, normally distributed. Has to say normally distributed, or we have to come up with some other method. All right, so the first question, What percentile are you in if you have a cholesterol level of 190? So we would take 190 minus 178 divided by 41, and we get 0.29. And if we come up here to the chart, notice we don't have a 0.29. This chart only goes in 0.05. So depending on the chart, if the chart you have is like 0.05 in this case or something else, and you can't get something exact, you can find a chart that has more specific breakdowns, or you can go ahead and just round it depending on what the assignment is. So in this case, we're going to round this to 0.3, and if your z-score is 0.3, you fall into the 61st percentile. So in this case, you are in the 61st percentile for cholesterol levels. And this is one of those cases where being in the higher realm is not a good thing. All right, if you're in the 90th percentile, what levels would you be? So we're going to come up here, and once again, we don't exactly have a 90.0. We do have a 90.3, so we're going to use that. And the z-score of 1.3 is the closest we have. So since we have the score and we're looking for the value, we're going to take x minus 178 divided by 41 equals 1.3. 41 times 1.3 is 53.8. Add the 178 and x equals 231.3. So if you have a cholesterol level of 231.3, you are going to need treatment. All right, so here are the breakdown of the SAT scores from 2010. Notice something. That looks like a normal curve. The SAT, ACT scores are normalized. Okay, that means most students score somewhere in the middle. The further you go out from the edges, the fewer they become. Okay, so most students are scoring somewhere between 1,300 and 1,700. And the higher up you go, the fewer and fewer students you have, and same thing with the lower that you go. Now, if you look at this really closely, you can notice it's not exactly quite symmetric. There are more perfect scores than zero scores. Just a few more, not many, but just a few more. But once again, real-world data isn't going to be a perfect match. Okay? But this is close enough that we can make it work. All right, so 5 questions. The highest score is 2,400. The lowest score in this year was 600. What's the mean? Well, I add those up and divide by 2. So 2,400 plus 600 divided by 2 is 1,500. So the average score on the SAT is 1,500. The median score is 1,500, and the most common score is also 1,500. All right, what's the standard deviation? So we are going to go, if we have to determine the standard deviation, we're going to go 4 deviations. So if you remember, 3 deviations was 99.7% of the population. We're going to go 1 more deviation above that to cover all of it. So 2,400 minus 1,500 divided by 4 is 225. And the reason we went from 24 and 15 is it's going to be 4 deviations from the mean to the high value. So 2,400 was the high value, 1,500 was the mean, and then divided by 4. So the standard deviation on the SAT is 225. So if a student scores 1,400, what is their z-score? So 1,400 minus 1,500 gives us negative 100. Divided by 225 is a z-score of negative 0.44. It is below the mean, hence the negative value. All right, if a student wants to get accepted into a specific college, they need to make an 80th percentile to get in. What score do they need? So if we go back to the z-chart that we had before, and we looked at 80th percentile, it has a z-score of 0.85. So that came off the chart from the previous page. So x minus 1500 divided by 225 equals 0.85. 225 times 0.85 is 191.25. Add 1500 to it, and you need a 1691 if you want to be in the 80th percentile on the SAT. And the last question is, what test score produces a z-score of negative 0.9? So we're going to take x minus 1500 divided by 225 equals negative 0.9. 225 times negative 0.9 is negative 202.5. Adding the 1500, we get 1297.5. And that is it for the normal curve.